We're nearing the end. In this section, we're going to explore the final and, in my opinion, the most important piece of JAX, it providing automatic differentiation on top of the NumPy API. So let's talk about this one function called grad. Grad is a function that transforms a function f into its derivative function. Now, with respect to taking in a function and returning a modified version of it, basically behaves a lot like VMAP. Here's a simple example. If we have the function 3x plus 1 defined in a Python function called func over here, we can pass func into grad, and it will return another function that has the exact same signature as the original func, except it will evaluate the gradient of func with respect to that first argument. So in this example over here, regardless of what value we pass into df, we'll always get back the answer 3.0 because that's what the gradient of the function f, the function func with respect to x is always going to be. Here's a slightly more complicated example, one that is a polynomial of x. Passing in the function polynomial into grad gives us back another function, which we're going to call dpolynomial, for which we can evaluate the gradient of polynomial at any value of x. So at this point, you might be wondering, why exactly do we want grad? I mean, we had very simple math functions for which the gradients are all analytically derivable. Well, think about the situation where you want to obtain the derivative of a function that calls other NumPy and Python functions a few layers deep. Deriving that gradient function by hand is incredibly tedious, right? By contrast, grad's ability to automatically transform the function into its gradient function by way of an automatic differentiation system is a highly convenient abstraction that eliminates the need for us to do any calculus by hand. Knowing that we can transform a function into its gradient function opens the door to do gradient-based optimization on any arbitrary NumPy and Python function. So for example, with a polynomial function, we can find the minima simply by taking small steps in the negative direction of the gradient. This is known as gradient descent, and it's well known in machine learning circles, especially amongst deep learners. For those of you who are inclined to think about probabilistic models, let's use the same ideas to do maximum likelihood estimation of parameters of a probability distribution given some data. This example, by the way, is available to us inside the Jupyter Notebook to peruse, and is a great example of how we can take the derivative with respect to two arguments rather than just one. So firstly, we'll generate some data from a Gaussian distribution, all right? Then we'll have to define the function that we wish to minimize. And in this case, it's the negative log likelihood of observing all of our data under the estimated values of mu and log sigma, which are the parameters of our Gaussian. Our function also accepts data over here, which we treat as a fixed entity not to be estimated. To minimize the negative log likelihood, we actually need the derivative of a Gaussian. Now, I don't know about you, but I'd find taking the derivative of the log likelihood of a Gaussian with respect to the Gaussian parameters to be a pretty tedious exercise, especially for someone who's as algebra blind as I am. But JAX now comes to our rescue. We can instruct JAX to give us the gradient, all right, of our log likelihood function with respect to both the mu and log sigma arguments by specifying the argnums keyword argument. And additionally, because we have data that we're conditioning our estimation exercise on, we partial it out so that we don't have to worry about it later when calling the gradient function. And now we can pretty much use the same optimization loop as we did before. We're now going to go on to the exercises. If you're feeling adventurous, please feel free to jump directly into the robot programming exercise right at the bottom of the notebook. Otherwise, I'd encourage you to really dwell on the polynomial example as an anchoring example. And as always, with computing ideas, definitely go ahead and break the implementation to see what happens, right? As it's one of the most effective ways to learn. With that, enjoy the notebook. It's our last one for this tutorial, and we'll see you at the end.